Hi everybody! In this video we are going to distinguish between two different kinds of rates of change. There are two main connected interpretations of the derivative, and one of those interpretations we've been talking about already is how you interpret the derivative in a graphical sense. So the first way that you can think of what the meaning or the purpose of the derivative is, as we've seen already, is in a purely mathematical sense of just the slope of the tangent line to a curve at a single point. So the first interpretation of the derivative, again, is graphically. And we use it to tell us what the slope of the tangent line to a curve is, again, at a single point. So we talked about this in detail already. In this section, we're going to look a little more generally about what the derivative can tell us through two different kinds of applications. So the second interpretation is when we kind of have a function that models a real-world situation. And when we are talking about the derivative in an applied sense, we don't really call it, slope wouldn't really make much sense in that context. So instead, we call it rate of change. In this section, we're going to look at two applications of rate of change. One of them is velocity, and the other one is what is called marginals. So velocity is really the application of the derivative to physics, of course. And the marginals is more of an application to economics, which we have already developed some things about economics in this class. So here we're going to see what the derivative and that can tell us about the economics applications in this course. So we have two different kinds of rate of change. We've got the average rate of change, and we'll abbreviate that as AROC or AROC. And then we have the instantaneous rate of change, or IROC. So you've actually already seen the average rate of change before, maybe in a previous math class, but also together we have talked about something called the secant line, or the slope of the secant line. So that is what the average rate of change of a function basically is. Again, we're just interpreting it in a more applied context. So the average rate of change, or AROC, of a function f of x, it goes from one point to another. Like we need a starting point and an ending point. So when we're talking about the average rate of change, we are talking about it over an interval from a starting point to an ending point. And the way that we would notate that mathematically is to make an interval like this. So let's just say that our starting point, we'll call this A, and we'll call our ending point B. So the average rate of change from A to B. And if you don't like that interval notation, you can also say the average rate of change of f of x from the input x equals A to the output x equals B. Okay, that's just what this shorthand interval notation is also saying. Here's what it is. So we're going to notate it as AROC, and then next to it, we're going to put the interval that we're finding the average rate of change over. So the average rate of change from A to B. Well, this is, again, no derivatives here. This is just the slope of a secant line, the change from one point to another on a curve. So it's just the change in y over the change in x. So we have a fraction here. Okay, the change in y over change in x is really what this is. So if I'll just go down to this graph underneath for a second and say, okay, well, if we have a point, let's call x equals a somewhere like right here. And this function here that we're graphing, this black curve, this is f of x. then the point on the curve that goes along with x equals a is right here. And so the output is going to be whatever you get when you plug a into the function. So we don't know what the function is. This is just a general formula. So this will be f of a. And then just say we've got another point, I don't know, maybe right here. Here's b. So we go up, here's the point on the function at x equals b. And the y value would be right around here. So here's f of b. The average rate of change is given to us by the slope of the line that connects these 2 points, and of course continues on in both directions. So the slope of it is going to be just the change in y, the change in the y values. So it'll be f of b minus f of a. That's just the difference in the heights between these 2 points. Okay, so it'll be f of b minus f of a for our change in y. Then in the bottom, that is just the change in x. So if we look on the graph here on the, the points that we're looking at, the change in x, the distance in the x direction between these 2 points, that's the distance between a and b. B is a larger number in this case, so we'll put b minus a for our change in x. So it's f of b minus f of a divided by b minus a. So there's no derivatives here. Okay, so for average rate of change from one point to another, and just note that there's no derivatives. This is just purely slope of a line between 2 points. So again, geometrically, the average rate of change is the same as the slope of the secant line between those 2 points that we have on, so a comma f of a, let's write that down, between a comma f of a. So that blue point there, x comma y, a comma f of a, and the green point, which would be b comma f of b. So what the meaning of this average rate of change, or why it's something that we talk about, well, if you think about going along the curve from this point to the next, the height is changing at different rates throughout, right? Like here it's kind of steep, then it kind of levels off, and then it starts even going down. So the average rate of change tells us that if we just wanted to go at a constant rate of change, right, this line has constant slope, a constant rate of change from A to B, the shortest path to get here, on average, if you took all the rates of change throughout all of these points here, or all of the slopes throughout all of these points here, they would average out to just be the slope of that line. Our other kind of rate of change is called instantaneous rate of change. So the instantaneous rate of change is the rate of change at an instant in time. We're going to call this IROC because it's a lot to write, instantaneous rate of change. So for the instantaneous rate of change, we just need one single point. So the instantaneous rate of change of a function f of x, but now at a single point, so at the one point that we need, x equals some number, we'll call that c. So this is just given by the derivative evaluated at that point. So we'll say IROC equals, and then f prime, the derivative, evaluated at whatever the point is that we want to find the instantaneous rate of change at. So if we're going to draw a picture of this, we just have this same curve down here. Say that, I don't know, this c value here, oh, again, so here's f of x. So say that the x value, which we're calling c, maybe lives right here. So the point on the curve is right here. The y value, which we actually don't need, but that would be f of c up here. Okay, the rate of change at this single point that we're looking at, the instantaneous rate of change, would just be the slope of the tangent line. So the slope of this line here. Okay, so geometrically, what the instantaneous rate of change can be interpreted as is the slope of the tangent line. to the curve f of x. Again, at the point, the single point, x equals c. Again, whatever that number may be. Okay, so what this can tell us, as we've seen before with slopes of tangent lines and such, it kind of approximates, if you look really close, just around this point, the curve, if you zoom in really far, it kind of resembles kind of closely a line. There's not really too much curving happening if you look really closely at a single point. And so this is why we can kind of really close to that point estimate it with a line, which we can find the slope of, and then say, well, the curve has about that same slope at that point. So we're going to need to kind of be able to distinguish between average rate of change and instantaneous rate of change given a problem or situation. We'll do that in just a minute, but before we get there, let's talk about the units that might be associated with different kinds of situations. Okay, so interpretation of rates of change depending on what your function measures as its output and what the input measures. So for example, if we have a function that measures maybe distance over time. So if you have a function that tells you how far something that you've tossed up has gone, how far from the ground it goes, a certain number of seconds after you've tossed it, that's an example of where your output measure would be distance. And this might, in general, measure something in miles. It might be like centimeters, it might be meters, it might be even like a really small, I don't know, micrometers, something like in chemistry where you're looking at things moving a really small distance. It doesn't matter. But just for the sake of having something to talk about, let's just say that this one, for example, is measured in feet. And then the input, what you put into that function, maybe that measures time. So you have distance at a certain time. Time, again, could be in days, it could be years, it could be seconds, it could be milliseconds. But just, again, for the sake of having an example of something to work with, let's just say that it's in seconds. Then the rate of change of the function, this can be average rate of change, or it could be instantaneous rate of change. The units that we would use to talk about the rate of change of your function in this particular case is going to be what you would find as the measure of the change in the outputs, which would be measured in feet, and then over the change in the inputs, which would be measured in seconds. So the rate of change of distance over time would be measured in feet per second. Okay, so change in distance over change in time. Well, this would be, and this is called velocity. So we actually have a word for this particular situation. Again, whether it's the average rate of change or the instantaneous rate of change, the average velocity or the instantaneous velocity, you're still looking at how distance changes over time. And the units for that would be the distance measure over the time measure, so feet per second, or miles per hour or whatever. If we are instead looking at a function that measures velocity, so the input to that would be feet per second, maybe miles per hour, whatever it is, and you are looking at a function that measures with its input as time, so you're looking at velocity at certain times, and just say again that we've got our time measured in seconds. Then if you want to find the rate of change of this function, that would be change in distance, change in velocity over change in time. Okay, so it's always the change in the output measure, which is like the y, over the change in the input measure, which is like the x. So the rate of change of your velocity over time, that's known as your acceleration. And this would be measured in the velocity units, which is feet per second, and then divided by the time units, which is seconds. So this would be feet per second over seconds. And we actually just abbreviate that as feet per second squared. Feet per second squared. I know it doesn't really make much sense, but really it's just feet per second. So this is really the extent for now of our physics, applications. Just talking about, velocity and acceleration. Our economics applications, we can also talk about the rate of change of cost, revenue, and profit. So say we're looking at a function that measures cost. So cost, of course, is measured in dollars. And the input, the x, right, is always the number of things made. So that would be our input is items made. If you wanted to find the rate of change, again, rather, either average or instantaneous, that's going to be change in cost over change in items. That has a particular meaning, and it's used a lot. So it has a vocabulary word or a term associated with it. This is called marginal cost. Marginal cost is the rate of change of cost depending on how many items that you make. So the units for that, again, are going to be the units of the output, which is cost, in dollars, and then per the units of the input. So that's items made. So this will be dollars per item. We can also talk about revenue and how the revenue changes depending on the items that you are, in this case, selling. So revenue, remember, is the money that that the producer makes. So if you have a shop, cost is what you pay to make your items. Your revenue is what you get from the customers. So the input for that is going to be the items that you sell. Remember, revenue is price times X, price of one thing times how many things you sell. So the input is how many things you sell or items sold. So you can look at the rate of change of revenue. This is called marginal revenue. And again, the units are going to be dollars per item. Okay, so it kind of gives you a sense of, more easy way to understand, like, how does your revenue change if you were going to sell one more thing? Like, what would be the increase in your revenue in that case? Same with cost. If you were going to make one more thing, what would your cost, how would it change? So slope is always a unit change in your input. You go over one, how much does y go up? And it's the same in applications too. If you change your input by one, if you sell make one more item or sell one more item, how does the cost or the revenue change? Okay, so it's dollars per one item would be the unit for that. Our last economics variable that we've been talking about is profit, again, measured in dollars. And the input is still X, but to make a profit, you've got to make and sell those items. So the input would, a little bit more specifically represent items made and sold. So if you want to talk about the rate of change of profit, change in profit over change in items, this would be called marginal profit. So again, another vocabulary or term to know what this means, right? It means the change in profit per item. Again, whether that is instantaneous, the derivative, or average, by just literally finding the slope or the change at two different x values, the units will still be the same. So again, we've got dollars representing profit, and items is your input. I guess we'll say dollars per item. So this would tell you how much profit will you gain or maybe lose if you were to sell one more item. So here we've got our economics part of this section. Okay, so just to, we'll talk about both of these. We'll do one example in a physics sense and one example in an economic sense. But I'd like to just go through one kind of more intuitive example that might help you kind of conceptualize a little bit what the meaning of average rate of change is. And I hope everyone can sort of relate to something like this. So if you're driving, say from Syracuse to Albany, they are 120 miles apart on I-90. If you were to make the trip in 1 hour and 40 minutes, of course, you are going different speeds at different times, right? You might speed up, like to pass somebody, you might slow down to go the speed limit again, you might even stop at a rest stop. But there is some kind of average speed that you were going. And so this is where you were, where your average rate of change would come in. Okay, so speed is pretty synonymous with velocity, except speed is always positive. It doesn't have a direction associated with it. So velocity could be negative, doesn't mean you're slowing down, it means you're going backwards, and a positive velocity would mean you're going forwards. But speed, it doesn't care about the direction, it just makes it positive, takes the absolute value essentially. It doesn't matter too much for this question, but just, that vocabulary, they're mostly the same, except in some situations, which I'll show you in just a minute. Okay, so if we're finding the average speed or average velocity, that's an AROC situation, right? AROC. And, right, this is going to be our change in distance because we're talking about velocity over change in time. Well, of course, the distance change, you went 120 miles. So that'll be our change in distance. The change in time, an hour, 40 minutes, well, that's not 1.4 hours because 40 is actually 2/3 of an hour, right? We've got 60 minutes in an hour. So let's just convert this into 1 2/3 of an hour. So if you divide these, if you actually take 120 divided by 1 2/3, you get a way of thinking about our speed or velocity that makes a little more sense. It's easier for us to think about. Like if you tell someone, I went 120 miles per 1 2/3 hour, that is really you're like, what? Like, tell me in miles per hour, right? So with these rates of change, one of the purposes is to get it in a unit that makes sense for us. Like per 1 hour, like what was your speed in that time, right? So if you just divide 120 divided by 1 2/3, you get 72. And the units are going to be, they'll stay the same. So we just divide these numbers, and then we've got miles per hour, per 1 hour, right? Because this is really like 72 over 1. So it'll be like 72 miles per 1 hour. So on average, that's how fast you were going. Of course, again, you went faster at some points, you went slower at other points, but on average, you were speeding a little bit, but probably not too much to get into any trouble. Okay, so in the next 2 videos for this section, we'll go through one example of a physics case and then one example with an economic situation involving velocity, marginals, and rates of change.